So Euler's method, it's the tangent line approximation multiple times. And I want to show you what that looks like. But just so you know, you need to have a specific point, once again, and you need to know how to get the slope. In other words, you need a differential equation, or you need the derivative. So assume that we have this point at 2, 1. This is our slope, and we're trying to estimate the value at f of 4, which is pretty far away. The error would be significant unless we use Euler's method. The first thing you need to do is figure out how far each little step is going to be. How many times are we going to make a little tangent line? How many approximations will we do? The more we use, the more accurate it would be. If I was doing this with a computer, maybe I would make each step 1/1,000,000th of a unit. But since I'm doing it by hand, I think I'll just use 4 steps. We'll go like half a step each time. Let me show you what I mean. So I'll let there be 4 steps. Let the number of steps equal 4. That means if you're going from an x value of 2 to 4, the distance between them is about 2 units. Take that 2 units in difference and divide it by 4 steps. 2 divided by 4 is 1/2. So the x values we're going to be using here would be these. Every half a unit, we're going to stop and recalculate the tangent line and use that to approximate our y value. So this is the way I like to organize it. It's a nice little chart here. And all you need is a starting point. Like I said, we know that there's a starting point at 2, 1. And then you need to know how to find the slope. So I want you to take that x and y value, the very first ones, plug it into your differential equation to find your slope. So that's great for telling us how much it changes y over x. I just want to know, how much does the y value change? And from the end of chapter 3, 3.9, you will recall that the differential of y is nothing more than the slope of the graph times dx, the differential of x. And how much does my x value change from this first stop to the second one? From the first tangent line to the second. The x value changes by 1/2. So I want you to take your slope, dy dx, times dx, or times 1/2. You've done the entire process now. Now you just have to do it 3 more times. Well, sorry, there is one more little step. You know what? If the y value is changing by 2.5 or 5/2, the y value was 1. Take 1 plus 5/2, and you have a new value there at 3.5 or 7/2. Now we repeat the process 3 more times. Don't forget how to do this. Take this new x and y value and plug them into your slope equation. That should tell you what the slope is going to be there. In this case, it's 8.5. Take your slope times the change in x. The x value is going to go up by 1/2, so I want you to take your slope, dy dx, times 1/2, and that will give you your new dy value, your new differential. That tells you how much your y values are changing. So knowing that this used to be 7/2 or 3.5, and now the y value changes by 17/4, you could do this in decimals, or you could do this as a fraction. I'm doing it as a fraction. If you have a calculator, which you would sometimes, you can do it this way, okay? Follow the steps and do one more iteration on your own. I'll check back in a moment. And oopsie, I actually wrote the wrong number in. The new y value, 3.5 plus 17/4, is 7 3/4 or 31/4. Now you can calculate the slope and the new change in y. Okay, so take your dy value, add it to your old y value. So this is the old y value. This is how much it's going to change by, and that gets you something like, oh, I don't know, 14 5/8. You only have to do this one more time. Try it with a calculator in decimal or fraction form. So you have your new answer. Is this the exact value? No, but using Euler's method, we can approximate it pretty well. And if you want to be more precise, take smaller steps to get infinitely close.